This video is just intended to finish up what we didn't finish in class today. I will do a quick review of cylindrical coordinates and then get in a little bit more detail in spherical coordinates, and I'll also take you through some of the examples. So watch as much or as little of this as you need to. As a reminder, the cylindrical coordinate system is basically just the 3D version of polar coordinates. So we bring r and theta over from our polar coordinates, and z is still the same z from our Cartesian coordinates. So essentially we're replacing the xy plane with our circular polar plane. The cylindrical to rectangular conversions, if we have r and theta, we can find x using r cosine theta and y using r sine theta, again, just like polar coordinates. So I'll just stick that here as a reminder, right? Just like polar coordinates. So it's the same x and y as in polar, and that comes directly just from right triangle trigonometry. And rectangular to cylindrical, again, same thing. These first two are directly from polar coordinates, and z equals z. So this is really just taking polar coordinates and putting it in 3 dimensions. Example A we looked at in class, and we talked about a couple of different ways to approach this problem, and it's entirely up to you how you do that. For me, I mentioned in class that I saw that I have a sine theta and a cosine theta, and I know that if I have r sine theta and r cosine theta, then I have an x and a y there. So I introduced an r, and I basically just multiplied the entire equation by r, and I got 4r sine theta minus 2r cosine theta equals r squared over x, and then I just replaced my r sine theta with y, and my r cosine theta with x, and the r squared with x squared plus y squared all over x, and I can simplify a little further by writing it as 4xy minus 2x squared equals x squared plus y squared. And then even further, if I wanted to, I could just set it all equal to 0, I suppose. So 3x squared plus y squared minus 4xy equals 0. And really, any of these forms is okay. Once you have it all in terms of x and y, you don't have to feel like you have to isolate one of the variables, because once you can isolate one, but you end up having it in terms of that same variable anyway. So any form is fine. And if you remember from class, there were multiple ways to approach this. We talked about possibly just multiplying by x and clearing that fraction. That's an appropriate approach, as well as simply replacing the sine theta and the cosine theta with x over r and y over r, or the other way around, y over r and x over r, respectively, for sine and cosine. So up to you how you approach it. Any way, there's multiple ways to get to the same answer. All right, so this next example we didn't do in class. It's asking us to convert the cylindrical equation to Cartesian and then identify and roughly sketch the surface formed. So this one, I have an r down here in the denominator, and it seems that actually if I multiply everything by r, I'm going to create not only an r squared, but I'm also going to create an r cosine theta and r sine theta, and I know that's going to help me. So 2r squared plus 6r cosine theta plus 18r sine theta equals 51. And then I'll replace everything. So this is going to become 2x squared plus 2y squared, right? Because r squared is x squared plus y squared. So I'll distribute that 2 plus 6x plus 18y equals 51. And this is looking somewhat familiar to me, right? I've got an equation in terms of x and y. There's no z. So that's hinting to me that it's probably some type of cylindrical surface. And if I want to go so far as to complete the square, it does get a little bit ugly, but we'll do it anyway. 3x 3/2 squared is 9/4 plus 2 times y squared plus 9y plus 9/2 squared is 81/4 equals, this is going to be 51 plus 2 times 9/4 is 18/4 plus 162/4. So I'll end up with 2 times x plus 3/2 squared plus 2 times y plus 9/2 squared is equal to whatever this sum is. I'm not going to do it right now. It's just some number. Okay, and now I can see that I do indeed have a cylinder. It's actually not just a cylindrical surface, it's actually a cylinder with, it's an upright cylinder. So the Z, it's standing up on the Z axis. So, and its center here is at -3/2, -9/2, and 0. So if I were to try to draw it, it's back here somewhere, right? -3/2 is back here, -9/2, I'm not going to fit it, but it's back in this direction somewhere. So it's something like that. Right? You don't have to worry too much about drawing it, just be able to visualize kind of where it is in the coordinate plane. So it's a vertical cylinder. All right, this last one we also didn't do in class, convert the Cartesian equation to a cylindrical equation. So now we're going in the other direction. The first thing I would do here is really just replace my x's and y's with r cosine and r sine theta. So x cubed is r cubed cosine cubed theta plus 2 r squared cosine squared theta minus 6z equals 4 minus 2 r squared sine squared theta. All right, and if I look here, this guy and this guy, I bet I can use a trig identity to simplify a little bit. So I'm going to bring those all on the other side, on the same side rather. So r cubed cosine cubed theta plus 2r squared, I'm going to factor that right out, cosine squared theta plus sine squared theta minus 6z equals 4. So we all know, hopefully, that this is 1. So this really just becomes r cubed cosine cubed theta plus 2r squared minus 6z equals 4. And that's it. That's a theta. That's it. Can't really do anything else in this case. Now moving on to the spherical coordinate system. As a reminder, this is kind of where we left off in class, but just as a quick reminder, the spherical coordinate system is the three coordinates are rho. Right, this little p looking thing is the Greek letter rho, our theta, which we know and love, and this is phi. And there is another way to draw the phi. It's like something like this. So either way, whatever you're more comfortable with, circle with a line through it or the little more fancy kind of script one is fine. So the theta is the same theta from cylindrical coordinates. And rho is actually just expressing the distance to a point, x, y, z, from the origin. Right? So it's just a distance, square root of x squared plus y squared plus z squared. So we've been doing, distance in 3 space for a while as well. As I mentioned, our theta is the same theta. It's the measure from the x-axis. And then phi is the measure of the angle that goes from the positive z-axis to you can think of it as a vector, or to the line segment that is drawn from the origin to the point in question. So the conversions are actually easier. This was I was mentioning in class, to start with the cylindrical to spherical first, because those tend to make a little more sense using trigonometry, and then we can back into the rectangular. So the cylindrical to spherical come directly from right triangle trigonometry. So let me see if I could, well, we'll have to kind of go back and forth here, right? I mentioned the theta and theta, it is what it is, right? There is no conversion there. Z equaling rho cosine of phi. If I look over here at my z, and I see this right triangle here, this three-dimensional, this right triangle is coming out at us, right? So my right angle is here, and I use simple trigonometry and simple geometry, really. I know that if this is angle phi, then so is this in my triangle, right? That's just parallel lines. Z is parallel to the z-axis, right? The distance, the z distance is parallel to the z-axis. So this is angle phi here as well. And that means that z is simply rho cosine phi. right here. And then similarly, and they express it as r squared, as the radius squared, but I could very easily have just said radius is equal to rho sine of phi. And so in similar fashion, if I look at my radius here, if I look along my radius, and rho sine phi, simple right triangle trigonometry, SOHCAHTOA, will give me my r, right? And then again, they just express it in squared. So now, and then I could kind of undo all of that to go from spherical to cylindrical. Now let's take a look at the rectangular. Okay, keeping in mind that in rectangular to cylindrical or cylindrical to rectangular, we know that, I'll put cylindrical here, right? X is equal to r cosine theta, and y is equal to r sine theta, and z is z. But so r cosine theta and r sine theta. Now let's take a look here. X in spherical is equal to rho times sine of phi cosine of theta. So if I go ahead and I look down here at my cylindrical conversion and I simply substitute this r into, I use a different color. If I substitute this r in here in both x and y, then I get my x and y conversions for spherical. And then z is still the same as it is for cylindrical. So that's where those conversions come from. And again, going the opposite direction, we're just undoing everything that we've already done. All right, now let's look at converting Cartesian to spherical equations. And if it helps to have those conversions up here, if you're not familiar with them yet, rho sine phi cosine theta for x, y equals rho sine phi sine theta, and z equals rho cosine phi. All right, so converting Cartesian to spherical, I'm really just going to do a straight substitution here, and see kind of what I come up with. So I've got rho squared, sine squared, cosine squared, and make sure you don't confuse your angles because it's going to be important in a minute to know what we're looking at. Sine squared theta equals, I'm going to have to write a lot smaller here, so 4 rho sine phi cosine theta plus rho cosine phi minus 2. And I see some things that I have in common here, right? I have a common factor of rho squared sine squared phi, and then I can see this cosine squared and this sine squared are going to just drop out, right? Because cosine squared plus sine squared is 1. So once I factor out that common factor and I'm left with cosine squared plus sine squared, all I really have left is rho squared sine squared phi is equal to 4 rho sine phi cosine theta plus rho cosine phi minus 2. And I think that's about really all I can do here. So these don't really turn out very pretty, so don't be alarmed. Obviously the Cartesian is something we're a lot more familiar with, and we can probably do a better job identifying the surface for most Cartesians. The spherical sometimes turn out pretty ugly. Now we're going in the other direction, spherical to rectangular. And I have a cosecant here, so I'm just going to rewrite that as 1 over sine of phi and see where that takes me. And it looks like it'll actually take me somewhere good because I have my cosine of theta here, I have my sine of theta, and if I multiply through by the sine of phi, I'm going to have something pretty close to what I need to do a simple substitution, right? So 4 sine phi sine theta. And if I look back up here at my conversions, right, I have that sine phi cosine theta, sine phi sine theta. All I'm missing is a rho, right, in order to get that x and y in there. So if I go ahead and now multiply everything through by row. I'm just going to change this 1 to a row. I'm going to stick a row in there, and I'm going to stick a row in there. And now I have an x, and I have a y, and then I can replace row with the square root of x squared plus y squared plus z squared is equal to 2x plus 4y. If I want to square both sides, I can and expand it. I don't have to. I can leave it right here. All right, so now here's where it gets a little interesting. So we want to identify the surface described by each equation. And some of these are easier than others, right? So if I think about what it means for rho to equal 3, if I think about my spherical coordinate system, if rho equals 3, this is saying that the distance from the origin to a point in space is always going to be 3. No matter where I am, right? If I come out, it's a little bit difficult to draw, hopefully not that hard to visualize, but if I go from the origin to a point in space, and again, keeping in mind I'm in 3 space, rho is always going to be 3. This is simply a sphere, hence the name spherical coordinates, sphere of radius 3. All right, this next one here says rho sine phi equal to 4. So if I remember some of my conversions, I know that in cylindrical coordinates, in the cylindrical coordinate system, rho sine phi is the same as r. So this is saying that the radius is always 4. Right? So my radius is always 4, and if I again think back to that cylindrical coordinate system, what does that mean? If the r value, I shouldn't have called it radius, the r value is always 4. The r value is that thing that lies right here. It's the projection of z, right? This projection of z. So this here is always 4 wherever I am. 4, wherever I am. So you can kind of see I'm forming a circle, and I've got no information about z, right? So I'm going infinitely in the z direction here. So this is a cylinder of radius 4. The other way to think about it is I could convert this to a Cartesian system if I want to, right? If I think of this, if this is rho sine phi, I can rewrite this as rho squared sine squared phi is equal to 16. And then I can, and this gets to be a little bit of a stretch, but if I add rho squared cosine squared phi to both sides, then I'm introducing a 1. Let me erase this here. Right? So this, again, this is a little bit of a stretch and a little bit harder to see personally, but rho squared, it's kind of like a proof here. Sine squared phi, if I decide somewhat arbitrarily, but not really arbitrarily, to add rho squared cosine squared phi to both sides, now I have a 1 here. So now I really just have rho squared is equal to 16 plus, and I recognize this is z squared. And we know that rho squared is x squared plus y squared plus z squared. So I have x squared plus y squared plus z squared equals 16 plus z squared. Those z squareds cancel, and I'm just left with x squared plus y squared equals 16, which we know in 3 space is a cylinder of radius 4. So either approach depends on your comfort level with the conversions and converting from one system to another. All right, this number 3 here says that phi is equal to pi over 6, right? And remember, I'm going to erase a little bit here. You can rewind the video if you want to see it. Phi is equal to pi over 6, and remember that phi is this angle here measured from the z-axis. So if that's pi over 6, it means no matter where I am along the z-axis, where I am on this surface, I'm pi over 6 degrees from the z-axis. So if you can visualize that, this ends up being a cone, right? Because no matter where I am, where I measure, and I can't really show this in 3 dimensions, but no matter where I am on this cone, I am always a measure of pi over 6 or 30 degrees from the z-axis. And then finally, theta is equal to 2 pi over 3. Think about where theta is. Theta is measured from our x-axis. If we measure theta from our x-axis here, and 2 pi over 3 looks like this. And so again, no matter where I am on my surface, I have to be 2 pi over 3 away from the x-axis. The only way this happens is if you can envision this plane. It's a vertical plane, right? Through 2 pi over 3. So this plane is just straight up and down vertical at an angle of 2 pi over 3 from the x-axis. And that's it. So again, my expectations right now, we're not going to use cylindrical and spherical coordinates that much, really. I don't believe, actually, I don't recall using them prior to getting to multiple integration. For right now, being able to convert an equation from one system to another, and then also really kind of being able to visualize these relatively simple surfaces in the different coordinate systems will be helpful. And that's it. Let me know if you have any questions.